So here at the Center for High Energy Density Science, our focus is to study plasmas at very high density and temperature. And one of the things that's very interesting about these plasmas, they access very exotic regimes. For example, these plasmas oftentimes have electrons which are Fermi degenerate or partially degenerate. The plasmas often act like liquids instead of gases. The plasmas often can support very high fields which will accelerate particles to very high energy.
What's really unique about the Texas Petawatt is that it has much more energy than all of the other petawatt class lasers in the world. So the Texas Petawatt, being a glass laser, has a longer pulse duration but much more energy. So we're typically at around 140 femtoseconds and 120 to 140 joules of energy to get our petawatt. It's at a university, and by being at a university, there's a lot of hands-on work being done by students. It prepares them very well for the large facilities around the world that are coming into being and being developed at places like Eli and ones coming on board in Korea and China.
Some of the things that's really cool in a machine like this is that it accesses such remarkable extremes. It accesses an extreme in power. You know, petawatt is essentially equal to 2,000 times the power output of all the power plants in the United States, but also accesses extremes in duration and intensity. So for example, if you take this petawatt pulse and focus it down to a small spot, we can create an intensity of over 10 to the 22 watts per square centimeter, which is essentially 100 times the intensity of the electromagnetic flux near a gamma ray burst, which is the most energetic event in the universe. So I can boast that in fact we have the brightest light in the universe here in our laboratory. The way we amplify such remarkable high powers, if I were to take a pulse like this and amplify it directly in traditional laser materials, I would drill a hole right down the middle of the laser, and this is not going to work. So the trick that we use is something that was developed, a very clever trick developed in the mid-1980s, which is to take a pulse that's short in time, which means it's broad in spectrum, spread the spectrum out in time before we amplify it, which means that if it were sound, it would sound like this. It means the pulse is chirped in color, amplify the pulse, and then undo the chirp and recompress it down to a very short duration.
Over the past 5 or 6 years, I have led a continuous series of experiments that have used the uniquely high energy and short pulse duration of Texas Petawatt laser pulses to capture about 1 billion electrons from a ordinary plain vanilla ionized gas or plasma and organize them into a tiny submicron bullet and accelerate them up to energies of 2 to 3 GeV, which is a job that would require an instrument 10,000 times longer with conventional technology and several hundred times more expensive.
As a graduate student here at UT Austin working on the Texas Petawatt laser, I've had the opportunity to take the lead on a couple of different experiment campaigns and have collaborated on many others. It's really great. A lot of grad students, our day-to-day activities are basically performing the experiments and dealing with the unique challenges of working with these high energy density plasmas because they're incredibly hot, dense, short-lived. We have to make them under vacuum, so they're really hard to create and probe. One of the great things about this facility is that it's both big enough that we can really perform cutting-edge research right here at UT Austin with all of the support and mentorship we need, but it's small enough that we grad students can really do the majority of the work and take leadership roles.
The goal of this experiment was to create the densest electron-positron plasmas and the most intense gamma ray sources in the universe.
Well, one of the things that excites me a lot about this is that much of the world is starting to move into this arena. There's some very large facilities being built in Europe. We have a lot of the expertise and a lot of the ability to help shape the future for those other facilities, to test out ways to make measurements at these extremely high intensities, to help teach them about the issues on optical damage, on maintaining the laser, and we should be able to participate with them, and we already have them coming to us to do work that will be valuable to them when they come online, over the next few years.
We're in an interesting state now. We actually have just recently received from Los Alamos a set of equipment from a laser that they shut down. There was a laser called the Triton laser at Los Alamos, which was a really useful and productive system over the years. We're now looking at expanding the capabilities of the facility we have now that would include much of the hardware from Los Alamos. And then along with that, we're looking at and we're talking with our sponsors back in Washington about the prospect of turning this facility into a true national user facility, which would open it up for users from anywhere in the world.